Hello and welcome to the third lecture on ordinary differential equations. In this lecture, I'm going to talk about some special types of differential equations that we are able to solve. This chapter in general is about first order differential equations. We cannot solve any uh, arbitrary given or first order differential equations. For some of them, well, actually, for a huge class of them, the majority of them, there is no explicit solution. However, for some types of first order ODEs, there exist some explicit solutions, and that's the main focus of this lecture. First order differential equations, well, uh, they are, it's because they are first order, we will only have one derivative of y, and the remaining will be just a function of t and y. That's by definition, if you remember, or the definition of order from last time. Okay, so again, this in general, we don't know how to solve. But one of the cases that we know how to solve is when this f, or the whole equation, is linear. Now, if you remember, to make this a linear equation, we need f to be a linear function of y and its derivatives. However, in this simple case, f is not a function of its derivatives, it's just a function of t and y, so we only need f to be a linear function of y. Remember, it doesn't need to be a linear function of t. So if you do that, if you force f to be a linear function of y, then you will get this equation over here. Well, in order to see this, you can just, if you replace f to be gt minus pt times y, this is the general form of a linear equation, of a linear function for f, then this is what you will obtain. Okay, so again, it's the equation here is y dot plus a constant with respect to y, so a function, a time varying function, which is pt, independent of y, multiplied by y, and then equal to gt. So how are we gonna solve this equation? You did see examples of this. Actually, both of our examples, the falling object and the population dynamics, are special cases of this. In those examples, though, both p and g were constants. Here we're going to consider the general case when they're time varying. The idea for solving this is to use integrating factors. And for that, we just want to make the first, the left-hand side here to be a function, or let's say to be the derivative of a known function. Because then I can simply take the integral and get rid of this, right? And we did this in both of the previous examples that we solved in the previous lectures. So for example, here, when we had this equation, we solved it by saying that, well, look, this is just the derivative of the logistic function. So I can just get rid of this by canceling out both sides. We want to do something similar here. Although it's not just that life is as easy as the equation here, that we can simply say the left-hand side is an ln function. Sometimes we need to use some integrating factors, which I explain now. The idea is to multiply this equation by some integrating factor, which we denote by mu of t, and then So basically I will have mu here, and then mu here, and then have this left hand side as the derivative of mu t times y. Of course y is also a function of t, but here we just want to emphasize that mu is not constant, so it's really y of t also. That's the whole idea. Okay, so in order to explain this, instead of just doing it in general, solving it in general, I will just go through three examples, and I will try to obtain it, to explain the solution step by step. Let's start with a quite straightforward example, example 3 here. So neither p nor g here are time varying, they're both constants. You should know how to solve this from the previous two examples. However, here we're not going to use the same method. We're going to use this idea of integrating factor. Okay, so whenever the question asks you to use integrating factor, you should basically follow 3 steps. Step 1 is to drive the equation for the integrating factor. How to do this? Well, first of all, again, the integrating factor is some function mu of t. Okay, first step, just multiply both sides by mu of t. So let's just multiply it here. So if you do that, you will see that we will get y of t times, let me simplify it by just writing y dot plus mu of t times 2y equals to 3 times mu t. So nothing special here, just multiplication. Now, again, the idea is to make this equal to d to dt of mu times y. Okay, so I want to make this to be equal to, hopefully I want this to be equal to d to dt of mu t times y. Okay, and well, what does this look like? Well, it will be first mu of t times the derivative of y, so y dot, then plus the derivative of mu times y. Okay. Okay, now if you compare these two equations, the one above and here, then you will see that these two terms are identical. Yay. And then by comparing the other two, you see that we have y dot of t equals mu dot of t equals 2 mu of t. Yes, sorry if I just mix mu and y. Yeah, this is simply by comparing these two. You see here and here. Okay? And this is basically the equation, the differential equation for the integrating factor. This is what I was looking for. It isn't a differential equation with respect to the integrating factor because it has the time derivative of the integrating factor here. And I'm done with step 1. If I can find a solution to this, then I can turn the left-hand side of this multiplied version in mu t of the original differential equation into a derivative of a form that I know the solution. Okay? So let me continue. The second step is, of course, to solve this equation, right? Solve the differential equation for the integrating factor. And you should know from the previous examples, this is quite straightforward to solve. Um, so for that, I will simply write it down as mu dot over mu equals 2, and therefore you should remember from the last lecture that this is ln of mu being equal to, d to dt. This is the time derivative of ln of absolute value of 2 equals to, you can also write down this part, this is the time derivative of 2 times t plus some constant c, and then again, if you recall from last lecture, I can now cancel out the dt's, then I will have mu will be plus minus the exponential of this term. I will have plus minus e to the power of c, which I will just use c prime, and then e to the power of 2 times t. Okay, so this is the general solution. Now, however, before I finish this part, you will see that in the third step, I will now then go back to this original equation here, and I need to solve this. So I just need to replace my general solution, right, which will be c prime times e to the power of 2 times t times y dot plus c prime e to the power of 2 times t times 2y equals to 3c prime e to the power of 2 times t. Now, you see that this c prime really doesn't play a role here. I can choose it to be anything. And actually, I can even cancel it out. When I'm gonna make this to be equal to d to dt of e to the power of 2 times t times y, hopefully that was what I was hoping for, then you see that having c prime here or not really doesn't matter, okay? You can just take it out of the whole thing and then cancel it out with this with the other c prime on the other hand side. So for this reason, we really don't need to worry about this coefficient c prime. Okay, and whenever I get to step 2 here, I can just say like we let c prime to be equal to 1, and then by writing this, then I will have the solution of mu of t, or just mu, equals to e to the power of 2t, just to make things simpler. Okay, if I do that, now I have my integrating factor. Yay. So now if I multiply it in the equation here, I will get this. Well, so far nothing interesting because it's just the same equation. I just multiplied both sides by e to the power of 2 times t. However, now this left-hand side is guaranteed to be equal to this. Now just test it out. The time derivative of this term, well, first, it will be e to the power of 2 times t times y dot, and then second, y itself times the derivative of this term, which will be 2 times e to the power of 2t. So you see that it's actually, these two actually are equal to each other. Okay. Okay, so let me erase these. By the way, what I'm doing here is just I'm using this this formula that's like x, y, the time derivative of this equals to dx to dt times y plus x times dy to dt. Okay, it's just the rule for derivative of a multiplication of two functions. So we don't need that. I suppose you all are familiar with these from calculus. So getting back to where we left, so the left hand side will be this, and the right hand side will be equal to 3 times e to the power of 2t. Now, I can also write this as the derivative of another function. So I want a function when I take the derivative, it should look like the one I have above. So for sure, I should have e to the power of 2t, because whenever I take the derivative of this, regardless of the factor that appears here as a coefficient, this factor 2 will not change by taking the derivative of an exponential function. So I will still, and I want this to be equal to the one above, so I will still use 2, but then when I take the derivative of this, I will have 2 appearing here, so I want something to cancel this 2 out and then get 3. So I will just use 3 over 2, okay? And then I will have some constancy. Good. Now I can just cancel both of them out, the time derivatives, and I will get e to the power of 2 times t times y equals to 3 over 2 e to the power of 2 times t plus c. Yay, this should be the solution. Just to finish this, so we will get y equal to 3 over 2, the e to the power of t's cancel out, and then I will have plus c divided by e to the power of 2t, which is equal to minus 2t, right? It's the laws with exponentials. Okay, good. So here we didn't have any initial conditions, so I will leave it as it is, but you now see the idea with integrating factors. We just try to find some function mu of t that when you multiply it in the original differential equation, you then turn it into this, the derivative of mu times y. That's the whole idea, okay? So far what we solved was very simple, because both 2 and 3 were constants. Now I want to continue with another example where this time it becomes a little bit more complicated, because then the gt here has an extra term, a time-dependent variable t. Okay, so let's proceed to example 4. For the following equation, find the solution that satisfies the initial condition y0 equal to 2 by finding an integrating factor. So again, we follow the 3 steps. Step 1, multiply both sides by mu of t and drive the differential equation for mu. And step 2, solve that equation. Now you see that this equation is very similar to what we had here in the previous example, just the term 1 over 2. Instead of 2 here, I have 1 over 2, and instead of 3 here, I have 2 plus t. Now, the point though is that when I multiply mu in this equation, and then I try to get, when I do the first step, I really don't care about the right-hand side. I just care about those terms that include y. Okay, so, and you see that this term 2 plus t, for the first 2 steps, I really don't care about them. I only care about this. Okay, so by multiplying mu in this and then doing all the same procedure, I will get the same differential equation, just that instead of 2, I will have 1 over 2. Okay, So I will leave this as a very simple little example for you to do, but then if you just repeat the equation, you will get mu t equal to e to the power of t over 2. Well, we will again get c prime times e to the power of uh, t over 2, but then you can let that to be equal to 1. Okay, so a little example for you to get to obtain mu of t. Now for the rest, it's also quite similar. I need to multiply this equation into mu by my integrating factor. So I will have e to the power of t over 2 times y dot plus 1 over 2 e to the power of t divided by 2 times y equals to 2 e to the power of t over 2 plus t e to the power of t over 2. Now this term here will be, I don't need to even calculate, this will be equal to e to the power of t over 2 times y, and then I will have the right hand side, right? So this will be d to dt of, yeah, so for calculating this, well, the first term 2 e to the power of t divided by 2, that's quite straightforward. I just need a compensation factor of 4 that when I take the derivative, it makes up for this 2. It makes up for this 1 over 2, and then we will get 2. That is straightforward. But for this other term, t e to the power of t divided by 2, we can play around with it. It's just, the idea is to use, we will need some t e to the power of t divided by 2 here, because otherwise I will not get this same term. So I will have t e to the power of t divided by 2, and so you can try it at home. You can try a constant a here, and then you will see if you take the derivative of this, you will have 1 e to the power of t over 2 term remaining. So you will need a second b e to the power of t divided by 2 to complete this, and then you can solve a and b, which by doing so you will see that a equals to 2, and the second term here will be minus 4. I suppose you know how to do these little calculations from calculus, okay? And then of course I need a constant c. Okay, great. So now I can solve this. I can just write down my final solution. Y equals to, I need to divide all sides by e to the power of 2 divided by t divided by 2. So I will have just 4 plus, by the way, you see here that the minus 4 e to the power of 2t's, they will cancel out, right? So what I will have here is 2t, and then plus this c divided by e to the power of t divided by 2, which will be c e to the power of minus t divided by 2. Great. Now, the only thing remaining is to use this initial condition of y0 equal to 2 and to get the final solution. So if I put 0 here, this term will be 0, and this will be 1, So I will have just c equal to y, which is just 2, the value of 2 here. So I will have 2 times t plus 2 times e to the power of minus t divided by 2. Great, this is the final solution. Now, you see that, well, this first one here, this was really the general solution, and the one here is the more specific solution for that initial condition, which was that at y equal to 0, at time t equal to 0, I had y equal to 2. So it's really this solution over here, right? Okay. Now you see that the solution of y, again, as a practice of being a good student, don't just jump into the next example like what we did here with example 3. We jump to example 4. Don't do that. Take a moment, try to digest. So we see that this is a damping term. It will just, as t goes to infinity, this term will go to 0. But then we have this new term that we didn't see in our previous 2 examples with the falling object and population dynamics, that it will just go to infinity as time goes to infinity. And how does it go? Well, it's like a line. It's just y equal to 2 times t. It's a straight line, right? So it's very similar to a straight line. And then other solutions are like this one here that we had. This specific solution, they are, with this extra exponential term, they are just converging to this line asymptotically. Okay. So this red one here is when we have c equal to 0. And the other ones are just exponentially growing. So as t goes to infinity, these solutions also go to infinity. However, how are they going to infinity? With what speed? With what rate? Well, they are going with this y equal to 2 times t rate. Okay. Okay, good. So far we learned how to deal with this first order differential equation, linear differential equation, when this second term was non-constant. Now, what if this one is also non-constant? And here is the example. It's t times y dot plus 2 times y equal to 4 t squared, and then you also have the initial condition. Great. So how should we solve this? I want to, the solution I want to provide here, well, I mean, first of all, we can divide the first equation by t to make it look like this for here, dy to dt plus pt. So I have all the time varying terms as a coefficient of y. So that's one option, which I will do here. You may try to just, without doing that, multiply both sides by mu of t for the integrating factor. But let me just first do what I suggested there. So the equation we have is ty dot plus 2 times y equals to 4t squared. Okay, so if I divide by t with the assumption that t is not 0, right? So if I assume that t is not 0, then I will get y dot plus 2 divided by t times y equals to 4t. Okay, good. Now the integrating factor. First, I need to drive the equation for the integrating factor. So that means I need to multiply both sides by mu. So I will get mu times y dot plus 2 divided by t times mu times y equals to 4 mu t. Good. Now, this should be equal to mu y dot plus mu dot times y, right? So from this, what color I should use? So from this, I get that mu dot equals to 2 divided by t times mu. And this is the equation for the integrating factor. Good. So the second part is to solve this equation. Okay? And I guess it's not difficult to see that for solving that, I will just divide it by mu. Okay? And then same story. So this is basically ln, well, d to dt of ln of absolute value of mu equal to 2 over t. You can also do d to dt. So what function was this that when I took the derivative I obtained 2 over t? So I always use the d to dt here. This time let's just I just write it down in another form. You don't need to always solve this. Sometimes you may not even know the solution for that. So what I will do is now I will take the integral with respect to t, and then I will have the ln of absolute value of mu equals to the integral 2 over, just let's use this notation s, and then with respect to t. And the initial condition can be 0 plus some constant c, okay? And then I can write down that mu equals to, well, again the plus minus sign, and then e to the power of c. All of that I will just simplify by having c prime here. And then I will, wow, okay. Wants to rush into the end of the lecture. So then I will have c prime times the exponential of the integral, right? So it's really e to the power of integral of 0 to t 2 divided by s ds, right? And this we know 2 over s is just ln of s. It's 2 times ln of s, right? When we take the integral. So this will be mu equals to c prime times e to the power of 2 times ln of the absolute value of t, okay, which now you see that 2 can go to the power of this absolute value, and then e and the ln will cancel out, so this will be c prime t square. And then again, so let c prime equal to 1, and then I will have how to do this. Okay, we'll have mu equal to t square. Great. So now we have the integrating factor. Okay. Now the final step. I need to multiply t squared into the original equation here, right? And then try to solve that. So if I multiply that equation, I can call it equation star. If I multiply equation star by t squared, then I will have t squared y dot plus, look what interesting thing is happening here. The t and the t squared will cancel out with this 2 divided by t, so I will just have 2 times t times y. It's nice to not have that 1 over t and have to deal with all those division by zeros, at least for now. And then I will have 4t to the power of 3. Okay, and no need to say that this is what I was looking for, which is d to dt of what? Of t squared times y. Okay. And it's not difficult to see that this is also d to dt of something easy, t to the power of 4 plus a constant c. Okay, now I can cancel out the derivatives, and then I will obtain y equals to t squared, I'm just also dividing by t squared, plus c divided by t squared, or t to the power of minus 2. Now we do have an initial condition. What was that initial condition? It's y at time 1 equals to 2. So if that means that if I let t equal to 1, I should have y equal to 2. Okay, so that means if I put 1 here, then I will have c here, and then I will have I should have 2 over here, so c should be equal to 1. That's a nice equation. Sorry for this. Okay. So that results in y equal to 2t squared plus 1 divided by t squared. Good. So how does this look like? Well, here. This is how it looks like. Now note that we did make this assumption of t not being equal to 0 in this very beginning. Okay. And if you recall the solution, now let's go all the way back to what we defined for a solution. You see, we say a solution is defined for an interval, and this interval is a continuous interval, and all those derivatives should exist at that interval. Well, here, in this example, this y, which is quite similar to that phi that we had there, is not defined everywhere. It's not defined for t equal to 0. So we can say that this holds for any subinterval of t in 0 and plus infinity, right? Or simply t greater than 0. I cannot say, well, this is my solution for, say, minus 1 to infinity, or in general, it's just for any t in R. No, because based on the definition of a solution there, we need to, the solution, the derivatives of the solution should exist for any number on that interval. So, no. Okay. So how this one looks like, so let me just get rid of this, what I wrote here. Okay. If you plot, you will get this. And this is the solution that passes the point 1 and 2. So t equal to 1, y equal to 2. Well, you see that this one is also diverging because of this t squared term. It's diverging, it's converging to infinity. It goes to infinity with a higher speed, faster than what we had in the previous example, because there we just had plus t, here we have t squared. And we have also this 1 divided by t squared term. And we know this one goes to infinity, but for values close to 0. So you see this solution is converging to infinity. It's just going to infinity for both values close to 0 and for when t goes to infinity. For t equal to 0, it's not defined. If instead, this is my general solution here, right? If, for example, if I have that at 0, it is equal to 0, then I will simply add c equal to 0 there, and I would add y equal to t squared. That was the simple second order equation which is this one. Okay. And for the negative values, it's just mirroring the one on the right hand side. So it's like here we have these negative equations. Okay. Well, that was just the post analysis of my solutions. Getting back to the main topic, we now know how to solve a first order differential equation when even both this coefficient and this term over here are non-constants, they're a function of time. That shouldn't be a problem anymore. So in general, going back to my main equation, which was in this form, y dot plus pt times y equal to gt. Now I know how to solve it. I just need to multiply both sides by the integrating equation, and by doing that, I know that this term should be y dot, mu dot over mu. You can just multiply it. It's again another practice for you to do at home. Then it will result in this term over here, and we can solve this by again doing that. This is by knowing that this is the derivative of the ln of absolute value of mu, and that will result in this exponential of the integral of p. I don't need to solve this. I can just leave it as the integral of this term p of t. Now, if this integral is known, then great, I have the explicit solution. Otherwise, I can just leave it as the integral. And then I will go back and multiply my mu into the original equation. And I know that on the left-hand side, I will have the derivative of this multiplication of mu and y. And on the right, I will have mu and g multiplied together. And then I will just have another integration, right? The left-hand side, this will just go away. And then the right-hand side, I will have the integral form. And the final solution will be this over here. Now remember that mu itself is here. So I actually have a double integrator. I mean, I have an not double integrator, but I mean I have an integral here, and I have another integral for mu. Okay, and this is the general form solution. Now, should we memorize this? No, you should not, and I advise not. You may, but you don't need to. Just so then what should we do? Well, whenever you see an equation like this, or the other examples here, just remember the idea. We just multiplied it by mu, and then we tried to obtain the differential equation for mu, and then we solve the equation. That's it. Even if you get this general form here, you know how to do it by doing that. Okay? So just remember that the main idea, and whenever you're asked to do that, just follow those steps. So far we're done with this idea of integrating factors for solving linear equations with variable coefficients. And the next part, I want to proceed to separable equations.